Today we're going to look at inverse functions, page 112, and the reason we're looking at inverse functions is because we are going to study log functions next, logarithmic functions, and those are the inverse functions of exponential functions. So if we can understand exponential functions and what an inverse is, then we'll be able to understand log functions a little bit better. And some of this information is usually covered in an Algebra 2 course, but I'm not sure that all of you have covered this information, so I'm going to go through it for you. So a function is a relation in which each x has only one y, or each input has only one output. The vertical line test, it tests for a function. So if a vertical line will only intersect a graph at one point, a graph once, then the graph is a function. And that's at any point. So if I start drawing vertical lines, I only want to cross my graph once. So let me give you an example, like a parabola. So that passes the vertical line test. If I draw the vertical line kind of anywhere along that parabola, right, I'm only hitting the parabola one time for each of those vertical lines. So what about for example, a sideways parabola? We learned about those in conics. If I draw a vertical line here, I hit two different points on my graph, and they would both have the same x value, right? Like this might be -2, 2. This might be -2, -2. So the same x value has a different y value. So that is not a function, and it failed, right? Failed the vertical line test. So that we've been using this year. So a function, right? So now we're going to talk a little bit about an inverse function and the horizontal line test. So an inverse function is just the result of exchanging input and output values. So you're just exchanging x and y. So if you start with AB on f of x, then BA will be on the inverse. So if you had 2, 7 here, 2, 7, then you would have 7, 2. You're just switching x and y. And there's a function notation that means inverse. It's this little f to the -1 superscript. So f of x is the original function, and f to the -1 of x is considered the inverse. It's not the reciprocal, it's just the inverse function. And if we're switching x and y, and that becomes y and x, domain of the inverse is the range of the original, and the range of the inverse is the domain of the original. So if we're switching x's and y's, then we're just flip-flopping domain and range. That should kind of make sense. All right, so what is a one-to-one function then? So if a function, each x has only one y, a one-to-one function, it has to be a function first, is a function in which each y has only one x. And the horizontal line test tests for a one-to-one function. So if a horizontal line only intersects graph once, then it's 1 to 1. So we're looking for the graph to be a one-to-one function. It has to pass the vertical line test first, then we can test it with the horizontal line test. If it has already failed to be a function, we're not even going to test it down here, right? Because this is for a function, one-to-one function. So let's give an example that would pass the horizontal line test. How about a linear function, right? Is it a function? Yes, it passes the vertical line test, and it also passes the horizontal line test, right? I only intersect the graph once with each of those horizontal lines. So it's a function, and it's one-to-one, and its inverse will be a function. So we're going to talk about this when we're talking about inverses. So what about our parabola? Our parabola was a function, but it fails the horizontal line test. So its inverse will not be a function. So I want you to think about the square root graph, right? The square root graph looks like this, right? If I dotted in the bottom half of this square root graph, wouldn't I have a sideways parabola? So even though we've got x squared and the square root of x, we consider those inverse functions of each other, but the square root function only has the top half of this kind of parabola graph, or else it wouldn't pass the vertical line test to be a function. So that's just kind of an aside. We're going to talk about that later. All right, so we talked about composition of functions last time. And so an inverse function will always yield the following result when composed. If you put g inside f, everything will cancel and you'll get x. And if you put f inside g, everything will cancel and you'll get x. So I wanted you to show that these two functions are not inverses of each other, and these two functions are inverses of each other. So let's do this one first. We're going to put g of x inside f of x. So g of x is going inside that x right there, inside f of x. So I'm going to do 3 times parentheses 7x plus 3 minus 7. Distribute, I'd get 21x plus 9 minus 7 is 21x plus 2. That is not x, right? So I don't even have to test this other thing, plugging f into g. It already failed being an inverse, right? I did the first test, I didn't get x. If I had gotten x, then I still should do the second part of the test and see if that comes out or if that fails. So in this problem, I'm going to plug this g of x now into this x first. So 1/2 2x minus 20 plus 10. So x minus 10 plus 10. Look at that. That came out to x. So I've done half of the test. Now I need to take this function and plug it in for this x. 2 times 1/2 x plus 10. So I did that part, minus 20. So now I'm going to distribute. I get x plus 20 minus 20. Voila, I get x. So check, check, they're inverses. So they both canceled everything out. I plugged one into the other, and then vice versa, got x. So now that we're going to look at two strategies on how to find inverses. So we've talked about what's the difference between a function and a one-to-one function, how to test if they're already inverses of each other. What if I just have a function and I want to find its inverse? So our first strategy is by graphing. So if AB is on the first graph, then BA is going to be on the inverse function. So the graph that they're giving me is 2x plus 5. We're going to see if we can figure out the inverse function. So 2x plus 5 starts at 5, 1, 2, 3, 4, 5 on the y-axis and goes up 2 over 1, up 2 over 1, down 2 over 1. So that's kind of enough points. So there's my first graph. So that's f of x. So I'm just going to record what these 4 coordinates happen to be. So this coordinate was -1, 3. So I'm just going to write -1, 3 over here. This point was 0, 5, the y-intercept. This point is at 1, 7. And this point is at 2, 9. So these are my points that are on f of x. Now I'm just going to flip-flop them, and I will get the points that are on my inverse function. So if I flip-flop this x and y, now I would have 3, -1, 5, 0, 7, 1, 9, 2. I'm going to do that in a different color. So I'm going to do my inverse function, I don't know if that's hard to see, in purple. So 3, -1, 5, 0, 7, 1, and 9, 2. All right, so there's my inverse function. So an inverse always follows this rule. The line y equals x is the mirror, and your inverse will always be reflected over that mirror. So if I just do a red function here, y equals x is really a slope of 1 and an intercept of 0, right? So start at the origin, up 1 over 1. So this is not an asymptote. This is just my mirror line, right? Y equals x. And all of these points have been reflected across that line, y equals x. So you just found an inverse by graphing. So we're going to do two problems where we graph the function and the inverse, and we graph the line y equals x. So if I graph negative 4x minus 1, I start at negative 1 on the y-axis, and I go down 4 over 1. 1, 2, 3, 4, and over 1. I'll go up 1, 2, 3, 4, and over 1. So let's just use those 3 points, let's say. So let's make a list of those 3 points. So I had the point negative 1, 3, and then I had the point 0, negative 1, and 1, negative 5. So if I'm going to flip-flop those, that was my original function. My new function is 3, negative 1, negative 1, 0, and negative 5, 1. So 3, negative 1, negative 1, 0, and negative 2, 3, 4, 5, 1. So here's my purple inverse function. And do those look like they've been reflected over the line y equals x? So this part of the line, right, has been reflected over, and this part of the line has been reflected over. So it has been reflected over. And it says, can you determine the equation of that inverse? I think it's easy to determine the slope, down 1 over 4, right? Down 1 over 4. So y equals negative 1/4 x. It's a little bit harder to figure out the y-intercept. So you might have to write it out as y equals negative 1/4 x plus b and plug in one of the points that you know. So remember, the point negative 1, 0 was on our line. So if I plug in negative 1 for x, 0 for y, isn't this positive 1/4? So b would have to be negative 1/4, so it adds up to 0. So 1/4 x minus 1/4. That must be going through the y-axis at, I guess it did go down 1 over 4, right? That was our slope, negative 1/4. So we're going to come up with an easier algebraic method to solve for this equation than just looking at the graph. Let's do the cubic function. You should all know the parent function for x cubed, right? 0, 0, 1, 1, and 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. It's kind of hard to see. And negative 1, negative 1, negative 2, negative 8. Here's the original function. So let's think about our points. We had negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, and 2, 8. So I'm going to flip-flop all those points, right? Negative 8, negative 2, negative 1, negative 1. These would all stay the same. 8, 2. So these 3 points stay the same right around the origin. And then 8, 2, negative 8, negative 2. Didn't I just graph the cubic or cube root function, right? So the cube root function is what I just graphed. Y equals cube root of x. Isn't that the inverse? They're going to undo each other. All right, so that's the first strategy is can you graph a function and its inverse? We're going to use this when we start looking at exponential and log functions. So the other strategy I wanted to show you was how to find an inverse algebraically if you swap x and y. So the first step is you need to have a y in your equation. So if it's written as f of x, you can just rewrite it so that it says y equals 2x minus 3 divided by 4. You're going to swap x and y in the equation. So x equals 2y minus 3 divided by 4. So coefficients stay where they are. I just switched literally the y and the x around. Now you're going to have to solve this equation for y equals. So we're going to multiply both sides of the equation by 4 to get 4 out of the denominator. So 4x equals 2y minus 3. What would be your next step to get y by itself? You'd have to add 3 to the other side of the equation. So now I've got that 2y equals 4x plus 3. So my last step is to divide everything by 2. So my inverse function of x is y equals 2x plus 3 halves, or 1.5, right? I divide this by 2 and get 2x. I divide this by 2 and get 3 halves, or 1.5. And then you could verify by plugging them into each other, but I'm not going to take the time right now to test that they're inverse functions. All right, so following the above steps, find the inverses of the following functions algebraically. So let's do these together. So if this was y equals, my first step is switching x and y. So x equals 3 times y plus 5 divided by 2. So now I need to get this y by itself. So if I'm multiplying by 3 halves, can't I multiply both sides by 2/3? And that will actually get rid of this 3, get rid of this 2. So I have 2/3 x equals y plus 5. So my last step would be to subtract 5 from both sides. So my inverse function, y equals 2/3 x minus 5. Or you could write f inverse if you wanted to. So again, this is y equals a cube root. So I'm going to write x equals the cube root of y minus 1. How do I get rid of a cube root? I cube both sides. So I'd have x cubed equals, now I have just y minus 1. So my last step is to add 1 to the other side. So y equals x cubed plus 1 is my inverse function. And you can kind of see how they're opposites, right? Cube root, cube, subtraction, addition, they're undoing each other. All right, so before you do the guided practice, which is finding the inverse down here, algebraically and graphically, I just wanted to show you how this is going to relate to exponents and logs. So let's just graph 2 to the x, which you should be familiar with, right? 0, 1, negative 1, 1/2, negative 2, 1/4. If I do 2 to the first power, I get 2. 2 squared, I get 4. So that's the 2 to the x parent graph. Hopefully that was familiar to you. If those are my key points, what did I just say? Negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, 2, 4, right? If those are my key points, then the log function, which is the inverse function, which you don't really know that much about yet, is going to go through 1/4, comma, negative 2, 1/2, comma, negative 1, 1, comma, 0, 2, comma, 1, and 4, comma, 2. So do you see how that purple graph is a reflection of the black graph over the line y equals x, right? So there's my mirror image, y equals x. Oops. This is the inverse. This is 2 to the x. We're going to see how this function is actually log base 2 of x. So we're going to see that graph a little bit more coming up pretty soon. So the same thing with the 3 to the x graph. Let's just graph 3 points. We know that -1 would be at a third, 0, 1, and 1, 3. -1, 1/3, 0, 1, and 1/3. So if I flip-flop those, I would be at 1/3, -1, 1, 0, and 3, 1. So here's my second log graph. This is y log base 3 of x because this was 3 to the x. So we're going to learn more about these log functions next class. And there's your reflection over the line y equals x. So the only page you need to submit today is kind of this back page because that has this guided practice problem. I'd like you to take this function and show me the inverse both graphically and algebraically. So you're going to submit just this one page so that you can show me this problem algebraically and graphically and submit it through the assignment in Google Classroom.